Last week, I heard a very interesting interview with Demis Hassabis from DeepMind, one of the two who recently won the Nobel Prize in chemistry. He said he believes that AI is going to eat up many of the use cases for quantum computing. If he's right, that's really, really bad news for quantum computing startups. Let's have a look.
But interestingly, I also have a slightly controversial take, which is, and I've talked to some of the world's top quantum computer scientists on this, is that actually I believe that classical Turing machines, classical computers, are capable of a lot more than we previously thought. Normally you talk about needing quantum computers to model any kind of classical system, but it may be that classical systems can model quantum systems. And I've tested this out with some of the people like Professor Zeilinger, who won the Nobel Prize in Physics recently for his pioneering quantum computing work. And, he thought it was very interesting. And David Deutsch, also one of my scientific heroes, who's basically invented quantum computing, said it was crazy, but the right sort of crazy, which coming from him, I take as a compliment and as also a sign to maybe pursue it further.
That artificial intelligence is a serious competitor for quantum computing isn't new, and a lot of people in quantum computing worry about it for good reason. The issue is in the exact way that quantum computers are better than conventional classical computers. It's not that they are per se faster, but that the algorithms scale better on quantum computers. You see, the quantum advantage comes from a curious property of quantum mechanics, which is that the space of possibilities is much larger than that you'd have without quantum properties like entanglement. If you use these many possibilities to encode your problem and work on it, then some problems are solvable with fewer operations. So that's the advantage, fewer operations. What this means is that when problems become larger, a quantum computer doesn't slow down as much as a conventional computer. But this doesn't necessarily mean the calculation is faster per se, because the operations on a quantum computer are usually much slower than they are on conventional computers. Supercomputer clusters now work in the exaflop range. That's 10 to the 18 operations per second. A quantum computer like Google's Sycamore, in the best case, would manage something like 10 million operations per second if it remained coherent for that long, which it doesn't. This figure summarizes the situation. Quantum computers have an advantage for some problems because they don't slow down as much with the size of the problem. But they have a huge starting disadvantage because they're so slow. They should catch up eventually, but just exactly when depends on how much conventional computers and the algorithms on them improve. And that returns us to Hassabis' remark. I believe what he's getting at is that you might not actually need this entire space of possibilities. So the advantage for quantum computers might be much smaller than expected. Because that's exactly what happened with AlphaFold, the AI system that cracked protein folding, and also previously with AlphaGo, the AI system that learned to play Go. In both cases, the space of possibilities is too large for a computer to brute force its way through by just trying everything out. For example, even if you take a fairly small molecule with about 100 amino acids, there are easily more than 10 to the 40 ways to fold it. So why did AlphaFold work anyway? It's because there are physical rules in the folding, so you don't need the entire space of possibilities. And the software learned these rules from the data. It's a similar thing for Go. There were rules to discover that vastly reduced the space of possibilities. And the same thing is already happening in quantum computing in one of the areas that's attracted the most interest, quantum chemistry. For this, one wants to calculate the properties of molecules or materials without having to produce them. If you can do that, it becomes dramatically easier, faster, and cheaper to find substances with desired properties for, say, drug development or battery technologies or catalysts that speed up certain chemical reactions and so on. It's commercially very interesting. And quantum computers are believed to be useful here because ultimately chemistry is all quantum physics. It's about electron bands and how they wrap around nuclei. But maybe you don't need a quantum computer to get the job done. Maybe a well-trained neural network with some physical rules will do. Indeed, just last month, a paper appeared in Science documenting how AI is filling in exactly this niche very quickly. The reason is, loosely speaking, that a lot of molecules and materials are quantum, but not a lot so. You just don't need all these possibilities that a quantum computer offers. Technology Review interviewed Giuseppe Carleo, a professor of computational physics in Switzerland and one of the authors of the Science paper. According to Carleo, quantum computers are unlikely to provide any advantage for most problems in chemistry and materials science. This is what I believe Hassabis was talking about, that there are certain natural systems, including some of the best use cases for quantum computers, for which there are physical rules that will make the problem digestible for a clever AI. That said, a more speculative interpretation might be that this isn't just the case for certain natural systems, but actually for all natural systems, including quantum computers themselves, once they get large enough, that they don't actually use the entire space of possibilities, but they are more strongly determined by some currently unknown physical rules than we think they are. You can see why I think that's interesting. If that was true, even just approximately, or in some cases, that'd teach us something very deep about quantum mechanics, though I'm not sure what. And if AI is good at making quantum computers superfluous, we might never find out. In any case, let me tell you something. When Hassabis said this, I was like, oh yes, why haven't I thought of this? Well, that's why he's won a Nobel Prize and I haven't. On the other hand, I'm on YouTube and he isn't, so don't forget to subscribe. The growth of civilizations is, for all we know, strongly correlated with access to energy. This is why fossil fuels have accelerated progress so much and why a lot of people understandably don't like the idea that we scale back on energy use. Indeed, astrophysicists speculate that we should be able to identify technologically advanced extraterrestrial civilizations because they would cover up their home star to capture its energy. But a new paper that just appears says that there are better ways to extract energy from stars, and we've been looking for aliens the wrong way. That technological advances are strongly correlated with energy use inspired the Russian astrophysicist Nikolai Kardashev to classify civilizations by their ability to use energy. It's now called the Kardashev scale and should not be confused with the Kardashian scale, which ranks civilizations based on their ability to stay relevant on Instagram. Actually, we're not so much concerned with energy per se, but with power. That's the energy that can be used per time. On the Kardashev scale, Type 1 civilizations use all the power available on their planet. That includes solar, but also geothermal, nuclear, wind, and so on. Estimates say that Earth could support about 100,000 terawatts of power. We currently use about 0.02% of that. So we have a long way to go and aren't even yet a Type 1 civilization. Once a civilization is using all the power that their planet delivers, the next obvious source of energy is their star. A Type 2 civilization harnesses the full energy output of their host star, like with a Dyson sphere. That's a megastructure which captures all the radiation coming off the star. A Type 3 civilization takes it a step further, using up all stellar bodies of the entire galaxy, stars, but also black holes. And the Type 4 civilizations finally use the power available in the entire universe. You see this summarized in this figure, which shows the relation between energy use per year and the size that the civilization needs to extend over. Earth is currently down here, and these orange dots are various future projections for Homo sapiens. As you can see, we're hugely underperforming. The Kardashev scale is usually interpreted to be about the radiation emitted by stars. Indeed, this seems to be why Elon Musk is so fascinated by solar power.
When you think in Kardashev terms, it becomes very obvious that the sun is overwhelmingly the source of energy, and everything else is tiny potatoes. Tiny, tiny, tiny potatoes.
The thing is, though, it's not true. You see, stars do nuclear fusion at a steady rate for a long time, and that's a convenient source of power, yes. But there is no physical reason why you can't generate energy much faster, resulting in more power. And most of the elements that can be fused to create energy in our universe are actually not in stars. They're mostly in interstellar and intergalactic clouds. This is where the new paper comes in. The authors point out that there are a variety of other ways that civilizations could grow much faster. They especially discuss stellivores, which literally means star eaters. These are civilizations that extract energy from their star by destroying it. And here I was thinking biosystem collapse is dark. One mechanism is what they call star lifting. For that, you remove materials from the outer layers of the star, for example, with strong magnetic fields. And then you burn it in a nuclear fusion reactor. The point is that this will create energy much faster than waiting for the star to burn through its fuel naturally. Another thing that a civilization might do is to drag matter from elsewhere to nearby the star and let it get trapped by its gravitational field. This will create an accretion disk like around a black hole. As the material spirals inward, it will release massive amounts of energy, far more than the star's natural light. If that sounds like science fiction, it's because it is. But it has implications for our search for extraterrestrial life. Because when astrophysicists look for technologically advanced civilizations, they look for techno-signatures. Besides actual radio signals with modulations that imply information transfer, this search has mostly focused on Dyson spheres and similar megastructures that a Type II civilization would build around their star. These megastructures would unnaturally dim the star, which is something that we can look for. However, if you take into account civilizations that are impatient enough to literally rip their star into pieces, you might want to look for something else. For example, stars that have accretion disks for no particular reason, or that seem to conspicuously shrink.
Tiny, tiny, tiny potatoes.
What bothers me about this is that if you'd asked people 2,000 years ago how we'd be generating energy today, they wouldn't have had any chance of getting it remotely right. So what are the chances that we're able to extrapolate the growth of civilizations for billions of years? Right. But hey, at least we're having fun with it. 10 years ago, a Hungarian lab reported a groundbreaking discovery. They found that the decays of some atomic nuclei disagreed with the current theories of physics. Their discovery made headlines as a potential new force of nature. Now a new paper reports they checked the observations. The 2015 discovery came from the Atomiki Institute and has been called the Atomiki Anomaly. Physicists at this place looked at what happens if you slam small charged particles like protons or alpha particles into a target that contains chemical elements with small atomic numbers like beryllium or helium. Sometimes the nuclei in the target will absorb the particles they've been hit by, and then, after some while, they'll decay. The type of decay the Atomiki people were most interested in was that resulting in an electron-positron pair coming out of a beryllium-8 nucleus. Using standard nuclear physics, they predicted the difference in angles between these particles, and that didn't fit the observations at all. They said that their result was incompatible with predictions at 6.8 sigma, which would be less than a 1 in trillion chance of it just being random noise. They assigned the observation to a new particle, which they called X17, because they calculated it would have to have a mass of about 17 mega electron volt. The paper was published in PRL, one of the top physics journals, but at first it was mostly ignored by other physicists. The reason is, I believe, that 17 mega electron volt is in an energy range that's been experimentally tested many times. If there was such a particle, it'd be hard to understand why it wasn't seen in other experiments. But a year later, a group of fairly well-known particle physicists lent credibility to the idea. They published a paper also in PRL saying they'd found a way that such a new particle might only show up in these nuclear decays and not in any other experiment that had been done to date. To paraphrase Ronald Coase, if you torture the maths long enough, it'll confess to anything. The popular science media was all over this, declaring it, as so often, evidence for a fifth force. I explained in an earlier episode where that phrase comes from. The excitement built when the Atomkey Lab reported in 2019 that they saw similar things in the decays of more atomic nuclei. Other research labs began experiments to see if they could reproduce the observations. That sounds very promising, but some things were very odd about this story. You see, the people from this lab had reported various similar anomalies previously, going back almost a decade. Some of those vanished with better equipment. Some vanished for no reason. Some were eaten by the dog. No, I made this up, but you get the picture. This lab doesn't seem to be hugely reliable. Then they announced they've seen a new anomaly. Would you believe it? Right. And that follow-up paper from 2019, that's a preprint which wasn't peer-reviewed. But, plot twist, in 2021, another group came forward with a calculation saying that the Atomkey observation was never incompatible with known physics. It's all standard physics. It's just that the maths is more complicated than you'd think. In their paper, they present the exact calculation and voila, it fits perfectly on the data. Actually, I think this calculation fits the data suspiciously well. Unfortunately, they don't say in the paper exactly how they did this calculation, just that it's partly numerical, so I can't check it. And the paper didn't get published. So this is super confusing. We're now not even sure it's an anomaly. And now this. Just last week, a result from another group appeared. This experiment was done by the MAC2 collaboration at the Paul Scherrer Institute in Switzerland. They did not confirm the anomaly. Instead, they ruled it out, but not at a high significance. You see the summary in this figure. This red cross is the original anomaly. These contours are where the new experiment searched for a signal and didn't find anything. That said, this result has a low statistical significance of just about 2 sigma. This means they reject the hypothesis of that new X17 particle, but not with much confidence. The reason is that they don't have a lot of data yet. This experiment will continue to collect data, so we'll probably see better results in the near future. What does this mean? Well, if you believe that the Atomkey result was actually standard physics, then we now have a new anomaly at low statistical significance. If you believe that the Atomkey result was an actual anomaly, which I think is the saner option, then the chances of new physics just sank, but not by much. There are various other experiments also looking into this. Basically, the current status of the X17 story is physicists are still extremely confused, but now with more expensive equipment. To summarize, we might have discovered a new particle, or not. Stay tuned for our next episode of the Anomaly Theatre. Physics just got a new problem, and it's a very interesting one. We've known for some while now that something isn't quite right with our theory for the universe at large scales. There are various tensions, but it's remained somewhat unclear how serious this really is. A new study now pinned down the origin of the problem, and they found a noticeable, if not huge, deviation from Einstein's theories. Physicists describe the universe as a whole with a model called lambda CDM, where the lambda is dark energy and CDM stands for cold dark matter. That's invisible stuff which allegedly fills the universe and should not be confused with Sabine's sense of humor. Lambda CDM, which is also sometimes called the concordance model, depends on 6 parameters from which we calculate predictions for quantities quantities that we can then measure. One of those is the Hubble constant. That's the rate at which the universe currently expands. Unfortunately, different measurements for the Hubble rate have resulted in different values. So there's simply no prediction from the lambda CDM model that fits all the observations. This problem is called the Hubble tension. There's a similar problem with another prediction that's for a quantity called sigma 8. Sounds like a student union, but it's a measure for how fast matter clumps in the universe. Sigma 8 has a similar problem as the Hubble constant. Different measurements have resulted in different values, so there is no prediction that fits all of them. Physicists call it the sigma 8 tension, but since that's such a clunky name, it's made headlines under the title that the universe isn't clumpy enough, or that it has a distribution paradox, or that it's too thin. No matter what you think about the status of theory development, and let me assure you I fully understand if you're not excited about it, I just find it so amazing that we even have these measurements to talk about. I mean, when I was a student, cosmology was basically philosophy. Now we have data from like a dozen different measurements. Cosmic microwave background, quasars, supernovae, gravitational lenses. Too bad for philosophers, I guess. For this new study now, they looked at gravitational lenses and images of big galaxy clusters collected by an experiment called the Dark Energy Survey. From this data, they extracted a quantity called the Weil potential. This is the combined deformation of space and time. It basically tells you how strong the gravitational potential is that light has to go in and then out as it passes by a galaxy or galaxy cluster. What you expect as the universe gets older is that these potential wells get deeper because matter clumps. We can use the lambda CDM model to calculate how they're supposed to get deeper. And you saw it coming, the calculation doesn't fit the measurement. The universe hasn't been clumping enough. As you can see in this figure, the fit to the data is, well, not great. Though there isn't a lot of data, which is why the statistical significance is not all that high, between 2 and 2.8 sigma. That's just about high enough to write a paper about. They also checked if the data can be explained by using some types of modified gravity, and the answer is yes. You see an example here, but I suspect there are various different types of modified gravity that would do that. By the way, this video comes with a quiz that lets you check how much you understood. What does all this mean? I think this is a very good development. This is because the data that give rise to the Hubble tension and the sigma 8 tension, they come from combinations of different data sets. These different data sets give us snapshots of the structures in the universe at different moments of time. And the tension is that these don't fit together with how the theory says they should change in time. The problem with this is that you're not sure whether the discrepancy is between the data and the theory or between the data sets. It's like if you have several portraits of the Queen at different ages and someone asks you if that's evidence she had a facelift. Maybe, or maybe one of the artists was very nearsighted. This new measurement now is giving us snapshots for the universe at different times from the same data set. That makes it much harder to blame the discrepancy on something to do with the data analysis. Assuming this is right, what do we learn from it? There are two possibilities. The one is that the lambda CDM model is wrong and we need another model within the overall framework of general relativity. This could be, for example, because dark energy changes in time, or because we need to take into account voids or something like that. The other possibility is that general relativity itself is at fault and that we need another theory. Einstein was wrong, basically. That said, I sometimes get the impression that if an astrophysicist has 3 different scales in their bathroom and they give 3 different results, he'll claim it's evidence for a modification of gravity. So this is very intriguing, but hold back the champagne. Thanks for watching. See you tomorrow.